No time. Okay. Recording in progress. Okay. Let us start uh, uh, our seminar today. Our speaker Kohei Motegi. Okay. You can start, please.
Oh, okay. Thank you very much for your introduction and invitation. And I'd like to thank the organizers for invitation to speak at this BIMSA Integrable Systems Seminar. So I would like to talk about some kind of, in some sense, some strange construction of Schur functions uh, using the idea of quantum integrability. So mainly I will explain two uh, main constructions. And first I will explain the result and see some examples. So the first one is a partition function which looks like this. So this rectangular shape, and we use, for example, the generation of rational R matrix, and the boundary condition is something uh, which may you have not seen before. So, for example, you can see uh, so for example, the left boundary, all states are n minus one,
Sorry,
and
maybe you explain this picture first. What is this picture?
yes, I will explain. So this is I use R rational degeneration of the rational I mean y a certain degeneration of YGL and R matrix, and as a local piece. And this partition function, so I use a, a degeneration YGL and R matrix. So there are in basis elements, and so you have, so basis vector are E1 from E1 to En. Sorry, E0 from, I use E0 to En minus 1. And so the subscripts 0, 1, 2, and to N minus 1 is sometimes in recent literature called as colors. So I will use the terminology color. And the left boundary, you use color N minus 1. And the right boundary, you use each color once. And you can see uh, bottom in the bottom boundaries, color 0, 1, and n minus 2, but color n minus 1 is not used. And in this top boundary, all colors are used. And if you compare the number of colors of the top boundary and the bottom boundary, you can see there are 3 zeros in the bottom boundaries and 2 zeros on the top boundary. So 3 minus 2 is 1. And also you can see in the bottom boundaries, color 1, you see 4 things colored by 1 and 3 parts colored by 1. So 4 minus 3 is equal to 1, right? So then you can see from color 0 to color n minus 2. In the bottom, the number of color I in the bottom boundary minus the color I in the top boundary is 1. And the exception is color n minus 1. And you can see color n minus 1 doesn't exist in the bottom boundary. And in the top boundary, you can see n minus 1 part color with n minus one. So and so that so I will show you an example. That this partition function gives this Schur polynomial if you use the degeneration of rational R matrix. And you can see this is different from the standard construction of non-intersecting lattice path or equivalently degeneration of Bethe vector. Uh, because, for example, the information of the Young diagram lambda basically in some conventional construction it exists only in the top boundaries. But in this case, the information of the Young diagram is not only in this top boundary, but also in this bottom boundary. Which I mean, if you want to change lambda, then you have to change not only this top boundary, but also this bottom boundary. So this is a very different construction from the Bethe vector construction. And also, there's a famous construction by Professor Kirillov called Fomin-Kirillov construction, and that's something which change. But I should say it's a little bit. I mean, it's different from also from that Fomin-Kirillov type construction, and. Hmm. And I should say, if you use the degeneration of rational R matrix, then you get this Schur polynomial. And if you replace that rational R matrix by a certain type of Q0 degeneration of the UQSL n hat R matrix, then what you get is the Grassmannian Grothendieck polynomials. So this is the first thing I want to explain. And the second one is three-dimensional. So this is a two-dimensional realization of Schur polynomial, and I want to. There is also another result which is not two-dimensional, but three-dimensional realization of Schur polynomials. So I will also show you an example of this thing, and so. Here, this kind of local piece is a Q0 version of operator valued stochastic. Operator valued R matrix introduced by Bazhanov-Sergeev nearly 14 or 15 years ago, and I will use a Q0 version of that, which was further studied by Kuniba-Maruyama-Okado nearly 10 years ago, and actually this you can see this kind of thing which I denote as X I Z one, and this is basically the same notation which Kuniba-Maruyama-Okado. And actually, this was a kind of thing was introduced in their work. Um, so their motivation was to study some kind of thing called steady state vector of multi-species tacit. But I use something in a different way. So I well, and I and so this is a joint work with Shinsuke Iwao and the Ryo Ohkawa, and and introducing and investigating this kind of partition function, and what you get is actually Schur polynomials with some overall factors. And well, I will explain the details about this later. And first, I will show you an example of this thing, which I explained the boundary conditions. But didn't see an example. So let's see an example. So the R matrix which I use is graphically represented as this. And this kind of thing is you can see this kind of thing, for example, in the paper of Gorosky, Washirev, Sotov, in their study of something called classical, quantum classical duality, so which they connect with something called goldfish model. And so I use this as a local piece. And an example of the partition function, which I explained is something with like this. So in the bottom boundaries, you can see two zeros and 1 0 in the top boundary. So 2 minus 1 is 1. And color 1 only exists in the bottom boundary and doesn't exist. So 1 minus 0 is 1. And color 2 is only on the top boundary. So this is one of the simplest examples which of the partition function. And for example, if you see this part, you can see there are two choices at the top right part. You have, for example, you have 2 0 or 0 2 here, and then if you see further, then you have in this part you have either choice 1 0 or 0 1, and if you think a little bit using by looking this figure for the R matrix, then you can find this first term is the remaining part of the first term is fixed. And also for the rest of the two terms, also the remaining part are determined uniquely, and the inner configuration is something like this. And then reading out the Boltzmann weight, or I mean matrix elements of the R matrix of each part and multiplying, then you can see the first term gives U1, U2, and the second term gives U1, U3, and third one gives U2, U3. And this is actually Schur polynomial with three variables, and the Young diagram corresponding is 1, 1, 0. And you can see for this kind of more complicated example, there are actually 8 configurations which which are non-trivial, and you can check by hand and check that this is exactly Schur polynomials with Young diagram given by 2, 1. And so this is some example of the first construction. And maybe I will be short of time. So I will first see an example of this second construction, I mean three-dimensional realization of Schur polynomials. So here you can see xi1 z1 and xim minus 1 z m minus 1 and xim zn, and the subscripts is actually count. So if you see this, you can see red parts which are colored by red and blue, and the subscripts mean how many parts are colored by red. So maybe I will. It's better to see an example later, but I think you can understand the rule of this subscript. And this subscript is actually here right, I1 is larger than I2 and I2 is larger than I3. But you can um, we also have the case when I1 is equal to or larger than I2. So you can relax this condition, but but for simplicity, I will sh just show this result. And and I should explain this operator valued R matrix or equivalently a three-dimensional R matrix. And um, so so first, forget about this dashed line. So if you ignore this dashed line, then you can see this is something. Uh, there are five non-trivial configurations. So this is if you ignore this Bazhanov, this dashed line, this is a five vertex model. But what is very different from what many people think is this to each kind each I mean each state I mean each configuration what you assign are not spectral parameter I mean but what you associate are operators. I mean, operators acting on Bazhanov Fuchs space. So, so for these two configurations, here I write one, but you should think these are identity operators. So for these two configurations, you assign identity operator. And for this third configuration, you assign a creation operator acting on the Bosonic Fuchs space. And this fourth configuration, you assign a annihilation operator. And in this last configuration, you assign something called zero number projection operator. And this is actually a Q0 version of a more generic operator valued R matrix introduced by Bazhanov-Sergeev. And these actually satisfy the tetrahedron equation, which is a three-dimensional generalization of the Ambexter equation first introduced by, I think, Zamochkov. And if you feel this figure is difficult to understand, I will show in this right one configurations which are non-trivial. So the dashed line means bosonic Fock space, and so the first two configurations means that this right part you have color M, and identity operator means that M doesn't change. Uh, so in this left part you also have color M in these two cases. And the third configuration is what is associated is a creation operator. So if you have color M in this right part of this dashed line, then the left part you get, so you create a particle. So I mean, so oh wow, I said color M, but you should think there are M particles, and you create a particle, so you now have n plus one particles. So here, so this left part you have color n plus one. So It's also similar with this fourth configuration. And the last configuration is zero number projection operator. So the only non-trivial three-dimensional configuration is if the right part is uh, color 0, then the left part becomes color 0. And for example, if you have color 3 in this right part, then this becomes 0. So this is a kind of an explanation of this operator valued R matrix or three-dimensional R matrix. And so ah and so and this some kind of operator xi z is actually a this kind of partition function constructed from this operator valued five vertex model introduced by Kuniba-Maruyama-Okado. And so these two boundaries are free boundaries, and so in this top boundary, you have um, uh, uh, you have a bunch of sequences of zeros and ones, and you count the number of ones in this top boundary, and you and that information, using that information, and you take this kind of weighted sum. So z to the power of number of ones on the top boundaries. And you consider every kind of configuration, and the subscript I means the number of uh, parts at this boundary, which are fixed to be color 1. And so, and you use this, we use this as, I mean, we basically use this, I mean, multiple times. I mean, and oh, sorry. So I think I didn't explain this. So this is so you can see dashed lines. So these dashed lines there are many. So there are actually many bosonic Fock spaces. And the right boundary you can see zeros, and you should think this is a vacuum state. So I mean, actually, a tensor product of vacuum state of the bosonic Fock spaces, and and to that you act xi_m_z_m, and then you act xi_m−1 z_m−1, and then finally you act by xi_1 z_1, and then finally I mean, you take the inner product between the vacuum state, or so and so this kind of thing gives the Schur polynomials. And let's see an example. And it's already difficult. I mean, it takes some time to check by hand by this very simple example. So this is well, using equation, it's something like this. And so you have vacuum state and x1, and then you act x3, and then you close with this dual vacuum state. And so let's see an example. So let's see this part which I circle. So this part you can see, so blue part, sorry, black part means that this is not yet determined to be red or blue. So if you see the configuration list below, then you can see this part has to be blue, colored by blue, and this part has to be colored by red, right? So from this fifth configuration, and then let's see this part, these parts. So this part which I colored gives a zero number projection operator. And so if you think a little bit, then this left part you have two choices. So identity operator or this annihilation operator. So, but if you think, but it you can see you cannot use this annihilation operator because vacuum state and so if you act a zero number projection operator on a vacuum state, you have a vacuum state, and acting a annihilation operator gives you zero. Um, so that this means that you can't use an annihilation operator here. So this means that you can use only an identity operator. So then you can find that these parts are colored with red. And so, well, you can't do play this kind of game. And so, for example, if you see this part, you can see this is blue, red, and if you see these parts, so these parts should be colored by blue because you cannot use a creation operator here. And then if you look this part, you can see there are two choices. So either a creation operator and annihilation operator here, or identity operator here. So you have two choices here. You have two choices. And then looking the remaining part, which are still colored by black, well, you can't see, maybe I should skip because of time, but you can see the remaining part are fixed uniquely, and also this second term also fixed uniquely, and then what you should do is so this is a weighted sum. Um, so you can see there are two red arrows going red arrows in the top boundary. So then from that part you have z1 to the power of 2, and from this part you also have two red arrows, so you have z2 square. And so in this second term you can see there are three red arrows in the top boundary. So from this you have z1 to the power of 3, and from this part you have one red arrow at the top boundary, so you have z2. So from these two configurations, you have z1 squared z2 squared plus z1 third z2. And actually, this is actually z1 times this Schur polynomial with Young diagram given by 2, 1. So this is an example of this second construction. And now I want to go back to part 1 and give a proof of the first construction. And actually, I will mainly the proof I will talk about the first construction, and the second construction, the proof is basically um, the same. So I will mainly talk about this first construction. So now let's go back to this construction, and so so I will use the technique of quantum algebra. And so to prove that this partition function gives Schur polynomials is based on this kind of multiple commutation relation uh, between this with the quantum algebra associated with um, this R matrix. So this is a commutation relation between a certain degeneration of the Yangian. So, so I will explain how to. I will actually see an example of this multiple commutation relation. So first we have to introduce notation. So, I think many people here knows about. Let us recall. So by multiplying our matrix, what you first think when you consider algebraic Bethe answers, for example, is you introduce a monodromy matrix, which graphically looks like this, and the matrix elements of the monodromy matrix with respect to this auxiliary space I denote as Tiju, and so there are m plus one square elements, but but in this proof I don't use everything. So I use only those which this left part is fixed to be color m. So then actually there are sorry, maybe. Oh well, anyway, so there are m there are m m plus one. I use only m plus one elements of this monodromy matrix, and I note this kind of thing as BKU, and if this right part is color M, I use DMU, but you can just, but maybe this was not a good notation, but let me use this. So, and as many of you know, from I the Yang-Baxter relation, you get this kind of intertwining relation between the monodromy matrices, which are called as RTT relation, and which looks graphically something like this. And for example, if you fix these left parts and right parts like this, then the left-hand side, you have this part are both colored by color M, and then you can see there is only one term coming from this left-hand side, and from this right-hand side, you have either color M and color J here, or either color J and color M here, and so then this first term means this and this second term using equation means this one. So you have this equation, for example. So bj u2 dm u1 equal to u1 minus u2 dm u1 bj u2 plus bj u1 dm u2. And so I think, of course, many of you know, but just for those who are not familiar with this. So then you can then rewriting um, you can have these kinds of a bunch of basic computation relations. So this kind of thing you can see in many papers of, I mean, general version you can see in many papers of quantum groups and Yangians. And so, and actually, you can see each term you only have two operators, right? And so, and we want to, and from this, you can then you consider this kind of thing. So you have dm from the left, you have dm and bm minus one, and finally you have a bunch of b0 operators. And what you want to do is to move dm operators, these bunch of dm operators to the right, and then so we want to switch the order of these operators. And so this kind of thing is you can see in these kind of computational relations are important in correlation functions business. And so for the case of UQSL2 or UQSLN or YGLN case, this is well, very complicated, but I use here a degeneration. So in this degenerated case, you can have this kind of fairly um, simple. I mean, maybe it's still a little bit complicated, but you can actually derive the exact form. And so one way is to use extend the argument of given in the paper of Shigechi and Uchiyama. Uh, but rather than explaining the proof, I think it's more illustrative to see an example. So let's see an example. So okay, so let's see this very simple. I mean, this simple example. So you have D2, B1, B0, and so you first commute D2 and B1. Then you have two terms, right? And then you want to commute D2, B, D2 U1 and B0 U3 and D2 U2 B0 U3, and then you get four terms. And then finally you need to commute B1 operator and B0 operator. So then what you get are eight terms. And so there are eight terms, but actually you can see some of them, the operator part is basically the same if you assume commutativity between operators of the same kind. So for example, B0 operator commute with B0 operator. So using something like that, there are eight terms, but actually they're actually some of them are basically the same. So you have six terms, and there are terms with which have only one term, but also there are things which have two terms, and you can simplify the coefficients. And actually, you can see they also factorize. And what you get is actually every term is actually looks like the thing in this bottom slide. So it basically looks like this, um, but the parameter in B0 inside B0 and B1 and D2 are actually what you see are permutation of these spectral parameters. And also basically the quotient looks basically almost the same, but actually they're some kind of sign factors. And taking that sign factor into account, you can write um, uh, uh, these six terms using this one. So this is the basic thing, and so W means you permute um, the spectral parameters inside this one. So this you can check by hand. So if you're interested, I recommend you to do this kind of computation by hand. So oh, sorry, maybe I should have sh show this slide. So you have two terms, but you can check this can be simplified as this kind of thing. So and anyway, you can show this kind of multiple commutation relation, and I will not explain the detail, but this kind of thing has something to do with symmetrizing. Ah, sorry. So now, keeping this commutation relation in mind, then I define this symmetrizing operation. So for a function, if u1, un, I define this symmetrizing operation as pi q1 qm star. And I take here as a definition, but actually there is meaning that of this operation, and this operation has a meaning of push forward of the cohomology ring of flag from the push forward from the cohomology ring of flag bundles to cohomology ring of non-singular variety or a point. Um, and but anyway, so then so then this key commutation relation uh means symmetrizing this partition function in the left gives you the um, partition function in the right hand side. So what's the difference? So difference is the right boundaries. So at the left hand side you have from the top you have zeros and then ones and then n minus ones, and finally you have color m. And this right hand side the order is reversed. So from top you first have color m, and then you have a bunch of color m minus ones, and then color one, and then color zero. So the order on the right part is reversed. So and this is actually easy to see if you derive the multiple commutation relations. So um, so using equation, this partition function is something. Uh, so can be written like this. So the bottom boundary I denote as vector j, and then on top of that you have this thing. So these are a bunch of DEM operators, and then you act Bm-1 operators and B1 operators, and then finally B0 operators, and then you close with this vector I. And push and in here you use the definition of symmetrizing operation. So then you get this expression, and so and then actually this sum of many operators are actually can be written as this single term, which the order of operators are reversed. So and this is and this last thing means this partition function. So this equation means the order of the right boundary is reversed. So so this is you can see, you can prove this thing. And well, I will not say in details, but you can also extend this right part and make that this right boundary are all colored by 0 only. But anyway, then now so to make connection with the Schur polynomials, let's take the simplest case of this one. Well, in this multiple commutation relation, you can have a bunch of zeros and B zeros and B ones, but for simplicity, I mean, to make connection with the Schur operators, Schur polynomials, I will use only one B0, B1, one B1, and one DM. So I will consider that simplest case. And then this symmetrizing operation can be written like this. And then if you are familiar with Schur polynomials, you can see this 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 one looks very similar with this determinate representation of Schur polynomials, right? So and so if you think a little bit, then you can observe that if you take this function, if you want um to be a product of monomials like this, then what you see is that symmetrizing this monomial gives you this Schur polynomial. Okay, so this is the second key observation, and so the key observation is that for a certain type of partition functions, which look very similar to with what I explained in the introduction, gives this monomial. So first I explained this bottom partition function. Partition function becomes Schur polynomial, and so what's the difference? So difference is that the right boundary, the order of color is reversed. So if you reverse this thing, then actually you can see this becomes a monomial. So this is the key observation. So let's see an example again. And first I explained we saw the case when the right boundary is from top color 210. But now here I reverse the order. So from top you have color 0, 1, and 2. And in this case, you can see that this part becomes 0, 0, and then this part, if you use a Yangian R matrix, then if you have 0, 1 here, you basically have two choices, 1, 0 or 0, 1. But I now use this kind of degeneration. So if you have 0, 1 here, then this part becomes 1, 0. So 0, 1 is not disappears. So here you have 1, 0, and then again, also you have 0 to here, then this part becomes 2. And if you play the same game, um, if you're interested, you can check by hand, and you can see configuration, which is non-trivial, is unique for this case. And then and you can also find this configuration gives you this monomial u1 4 times u2 squared. u1 to the power 4 and u2 squared. And so this means that symmetrizing this fact and so the result for a symmetrizing operation, which I explained before, means that symmetrizing this partition function, which is actually a monomial and it's u1 to the power of 4 and u2 square. So for example, so this means that symmetrizing that kind of monomial gives you a Schur polynomial. So first, you can see that symmetrizing this partition function on the top gives you this Schur polynomial S21, and on the other hand, by using the multiple commutation relation between the quantum algebra, symmetrizing this partition function becomes this partition function, which the order of color on the right boundary is reversed. So the two computations mean that this partition function is represented by the Schur polynomial. So you can see this in this Rumsfeld book for more details. And so and so the fourth this figure of R matrix element. So if you change the bottom part slightly a little bit by this, then so this one you can regard this as a Q0 degeneration of a version of quantum UQSLN at R matrix, or are today now called as stochastic R matrix. So you use a Q0 version of stochastic R matrix, and then if you consider the partition function with the same pattern, then what you get is not Schur polynomials, but instead a Grassmannian Grothendieck polynomials. And proof is, well, actually basically the same. And so these kind of things are related with the k-theoretic push forward, but anyway, proof is basically the same. And okay, and also next
Sorry to interrupt. We have 5 minutes left.
oh, okay. I will finish in 5 minutes. Okay. So this second construction, using a three-dimensional R matrix. Well, we saw a simple example. This partition function gives Schur polynomials, and this holds for this kind of more generic for this generic case. And and actually, proof is basically the same. And um, so in the first part, we used what was the key was the multiple commutation relation, and that was constructed from more basic commutation relations, which come from the RTT relation, and actually, so in Kuniba-Maruyama-Okado's paper, they actually showed a similar relation. So these are actually RTT equals to TT type relation. So Adif Zamolchikov type relation. So it's a little bit, basically a little bit different from RTT relation, which is RTT equal to TTR. But for this Q0 case, basically the commutation relation they showed are very similar. I mean, it's a little bit different, but basically it looks very similar with the commutation relation which I showed. So I can use we can use the argument by Shigechi and Chiyama again, and you can derive multiple commutation relations. Uh, and and also you can see also you can see, so in this example, I1 is equal to or larger than I2, and I2 is larger than equal to I3, and so and if you reverse the order, so here I1 is I2 is larger than or equal to I1, and I3 is larger than or equal to I2. And in that uh, case, the other extreme case, and you can see there is only one non-trivial configuration. So, um, so I think it's fun to see an example by hand. So if you're interested, you can check by your hand. And you can check, you can show there is only actually one launcher configuration in this case, and it's actually from that configuration you have this very simple monomial, and then in the way which is basically the same with which I explained for the first construction, you can show this um, this this partition function becomes a Schur polynomial uh, with some overall factor. So this overall factor comes from the slight difference of the multiple commutation relations. So this is essentially the same width, or but a little bit different. So that results in this kind of overall factor. Um, hmm. But it's essentially proof is basically the same with the first construction. And and also in our paper with Iwao and Ohkawa, we consider some kind of inhomogeneous generalization, and if you so that doesn't respect the quantum integrability, but you can show in simplest cases. So partition functions become something called loop elementary symmetric functions, which appeared in Yasuhiko Yamada's work in the classical discrete total lattice. And so there are many. So 3D partition function is not the much is much less studied compared with two dimensional thing. And so I think there are many things to be done. So maybe I have no more time, so I think I should stop here. So thank you for your attention.
Okay, thank you for your talk. And questions?
You see, so many calculation you did. So first, two questions I have. First question. So what's the origin of this symmetric function first? What's the origin? And second, what we have to do and what we learn from this symmetric function, what we have to do with that? Yes, learn and do.
You mean Schur function?
Yes, I mean that what's the origin of the symmetric function? Symmetric to the states or what? What is the origin? In your opinion, you look many examples, right? Different symmetries of the R-matrices. What's the origin of this symmetric function?
Origin.
Yes. Bethe vectors.
So these partition functions are, as far as I understand, doesn't have to do with Bethe vector. So for example, maybe I should. So for example, of course, you know that Bethe vector is constructed by acting, for the simplest case, acting B operators on vacuum state, right? But the bottom part, this construction, first of all, you don't use a vacuum state. So if it's a vacuum state, then every part should be color 0. But this actually begins from some state which is not a vacuum state. So in that sense, that's very different from the standard Bethe vector construction. So, and also this bottom part contains the information of Young diagram. So the standard Bethe construction. So you have a vacuum state and then acting B operators, and then you have a bunch of zeros and ones in the top, and the position of ones counted from left basically corresponds to the Young diagram. I mean, so if you want to change lambda in that construction, you just need to change the sequence of zeros and ones on the top boundary. But in this construction, if you want to change lambda, you have to change both the top and bottom part. So that's very so this construction, I think, is natural from the point of view of push forward. So symmetrizing operation has the geometric meaning of a push forward. So, and push forward is naturally related with the multiple commutation relations, which I explained. So, in that sense, from that point of view, I mean, from the point of view of push forward, or Gaussian map or something called like that, this construction is natural. But it's, of course, strange.
Son, I want to ask you some maybe technical questions. I really don't understand how you prove that how Grothendieck polynomials appears, because I don't see any determinantal formula for Grothendieck in your talk. How you prove?
Sorry, I haven't prepared that much, but the proof is basically same. I mean, so
Property of Grothendieck you use divided differences, or what interpretation?
So I see in several papers, for example, Nakaga Naruse, so in their paper, what they showed, you can see a more generic version, and so symmetrizing, well, actually symmetrizing not monomials, but symmetrizing some kind of a simple things which are close to monomials gives you Grassmannian Grothendieck polynomials. So basically,
but I don't see appearance of parameter beta. It's hidden in spectral.
Sorry. Beta is I think said to be -1 or 1. I mean, so if you use UQ at the R matrix that and consider Q0 degeneration, you can give that corresponds to beta -1 case. And yeah, but you can use some kind of gauge transformation. I mean, something called, I think, Reshtikin twist. Then you can include that kind of parameter. So there is actually some paper by Brubaker and his students about something called frozen pipe something. So using that kind of thing, you can also introduce parameter beta, I think.
Well, and I just wonder, you use combinatorial formula for Grothendieck polynomials when it means positivity, or just determinantal formula?
Sorry, positivity.
Okay. And I just ask questions. You wrote certain rather general identity, some divided difference operators, X, some nice. Does this include another generalization of Grothendieck polynomials, two-parameter Grothendieck polynomials? This is called the Hecke Grothendieck case.
Well, at least this case doesn't have two points. I mean,
I just wonder what is the generality of this construction. It is just how to say, you can cover only Schubert polynomials, but I don't see any permutation with Schubert polynomials depends on commutation, not only for lambda.
This construction only Grassmannian.
Okay, anyway, thank you very much, Motegi-san, for nice talk.
Thank you.
Okay, let's thank the speaker again.